Welcome to my channel Phi Concepts CHM. We will see the fifth part of semiconductor diode characteristics. Here we will see the quantitative theory of PN junction diode currents. Quantitative theory of PN junction diode currents. We will find the expression for total current as a function of applied voltage, that is the volt ampere characteristics. In the forward bias PN junction, the quantity is related to the hole concentration in the in-N region due to minority carrier injection such as Pn of X. This can be said as Pn of X, Pn dash of X. This is corresponding to X is equal to 0 and Pn 0, etc. are shown in this figure. It follows that the excess concentration at X is equal to 0 is given by Pn dash of 0. This is Pn dash of 0. This will be equal to Pn of 0. This is Pn of 0 minus this Pn 0. So this Pn dash of 0 is equal to Pn 0 minus Pn 0. Pn 0 is the equilibrium concentration. Now the diffusion hole current in the N side is given by IPN of X is equal to AE dP by LP into Pn dash of 0 into e raised to minus X by LP. This is the injected concentration. Equation 1. Here IPN depends on the applied voltage through the factor Pn dash of 0, the injected concentration which is the function of voltage. Law of junction. In forward bias, the barrier height of PN junction lowers, allowing more majority carrier to be injected to other side as minority carrier. The minority carriers, such as the holes at the junction of N side, that is Pn of 0, must be a function of applied voltage V. Consider only the hole current. Across the junction, due to rather high electric field, the hole drift current is large, and due to high concentration hole diffusion current is also large. Let us consider the low level injection caused due to bias voltage. The net hole current density Jp will be the algebraic sum of two current components. Jp is equal to Ep mu p into E, this is the drift current, minus E dP into dP by dx, this is the diffusion current. Equation 2. Further, Ep mu p E is equal to E dP into dP by dx. This is, we are considering for a case of low level injection. We mean that due to low bias voltage, the net hole current Jp is very small. We can take it as approximately 0 because both the terms on the RHS of equation 2, that is these two terms, they are however large but nearly equal, hence Jp becomes very small. And also as E is equal to minus dV by dx and dP by mu p is equal to kT by E, this is equal to the volt equivalent temperature V suffix T. The above equation becomes, so we are substituting all this in this equation, we get minus dV by dx is equal to dP by mu p into 1 by p into dP by dx. Then this can be written as dV is equal to, we are substituting this Vt over here for dP upon mu p, so that will be minus of Vt into dP by p. Let Pp and Pn be the hole concentrations at the edges of space charge region in the P and the N side respectively. So Pp and Pn. Let Vb be the net barrier potential across the junction. Then integrating the above equation, we get integration of dp by p from pp to pn is equal to minus 1 by vt into integration of dv from 0 to vb. So we get ln pn upon p0 is equal to minus vb upon vt. We can rearrange this equation to write p and pp is equal to pn into e raised to vb by vt. Equation 3. Now this equation is valid under equilibrium as well as non-equilibrium condition. That is, as long as the net hole current Jp is small compared to the diffusion current and the drift current due to the holes. We'll see two cases. One is in the open circuited PN junction. In equilibrium in the P region, the concentration of the majority carriers, that is the holes, which will denote as PP0. So here it is PP0. And the minority carriers as electrons will denote as NP0. Similarly, for the end region also you will get these terms NN0 and these quantities NN0 and PN0 respectively. Thus, in this case, PP will be equal to PP0 and Pn will be equal to Pn0 and Vb will be equal to V0, which is the potential barrier for the open circuited PN junction. Therefore, this equation 3 will become PP0 is equal to Pn0 into e raised to V0 by Vt. Equation 4. Similarly, we can write down for with Nn is equal to Nn0 and Np is equal to Np0 as Nn0 is equal to Np0 into e raised to V0 by Vt. Equation 5. Now, second case, the junction is forward biased with voltage V. Then the barrier voltage Vb will be V0 minus V. It will be lowered. Equation 3 then takes the form just in place of that Vb, we have to just write down V0 minus V upon Kt. Pn0 will become Pn of 0 because this is the injected concentration when we are applying the forward bias voltage. So it will become Pp0 is equal to Pn of 0 into e raised to V0 minus V by Kt. Equation 6, which is the Boltzmann relation where Pn0 is a minority concentration near the edge at x is equal to 0 and the other quantities remain constant. Comparing now equations 4 and 6, we can equate them. We can write down Pn0 into e raised to V0 by Vt is equal to Pn of 0 into e raised to V0 minus V upon Vt. Split the powers of this exponential into e raised to V0 by V into e raised to minus V by Vt. And rearrange this equation, this will cancel out, e raised to V0 by Vt, and we get Pn of 0 is equal to Pn0 into e raised to V by Vt. Equation 7. This equation is called as a law of junction. It shows that for the forward bias V get greater than 0, since the exponential is greater than 1, a minority hole concentration at the junction Pn of 0 will be greater than the thermal equilibrium value Pn0. A similar law can be obtained for electrons, that is this law. Equation 8. From equation 7, Pn dash of 0 is equal to Pn of 0 minus Pn0. So we can substitute Pn of 0 and we will get Pn0 taking common into e raised to V by Vt minus 1. Equation 9. From equation 8 also we get similar type of equation. Np dash of 0 is equal to Np0 into e raised to V by Vt minus 1. Equation 10. Forward currents. Using the equation Ipn of x is equal to A into Jp is equal to Ae into dP by Lp into Pn dash of x. We will take at x is equal to 0, Ipn of 0 is equal to Ae dP by Lp into Pn dash of 0. Substituting for Pn dash 0 from equation 9 that we have just got, this equation will become, we are substituting of Pn dash of 0 here as Pn0 into e raised to V by Vt minus 1, equation 11. Similarly for electron we can write same kind of equation, equation 12. The total current is then given by I is equal to IPN of 0 plus INP of 0. So we'll substitute both of them here. E raised to V by Vt minus 1 is taken common and AE also is taken common. So in the bracket you have dP by LP into Pn0 plus dN by Ln into Np0. Or we can write down this equation as I is equal to I0 into E raised to V by Vt minus 1, equation 14, where I0 is all these constants AE into dP by LP into Pn0 plus dN upon Ln into Np0, equation 15. So equation 14 will give the total diode current. So in this derivation, the depletion layer width has been neglected compared to the lateral dimensions of the diode. Equation 14 is, we'll see now the reverse saturation current. Here equation 14 was derived for positive voltage, that is for forward bias. The same is valid for the negative voltage, that is reverse bias. So for reverse bias, mod V, V is negative, so mod V is greater than Vt, so the exponential will be less than 1 and I will tend to minus I0. I0 is called as a reverse saturation current. Using equations for concentrations in equilibrium state, namely the equations of charge densities in semiconductor, we get Nn0 into Pn0 is Ni square, and Nn0 is approximately equal to Nd, the density of the donor ions, and Pp0 upon Np0 is equal to Ni square. So, and Pp0 is approximately equal to the concentration of the acceptor ions Na. So we can write down Pn0 from this equation. From this equation, Pn0 is equal to Ni square upon Nn0. We are substituting Nn0 as Nd. Same way, Np0 is Ni square upon Pp0, and in place of Pp0 we are substituting Na. So these are equations 16. Substituting this in equation 15, we get I0 is equal to Ae into dP by Lp into Ni square upon Nd plus dN upon Ln into Ni square upon Na. Ni square is taken common over here, equation 17, where Ni square is A0 into T cube into E raised to minus Eg0 by Kt. In place of Eg0, you can substitute Vg0, equation 18. We will apply these relations to the germanium and the silicon diodes. First, for germanium diode, the diffusion constants dP and dN are inversely proportional to temperature. So from equation 17, as I0 is proportional to Ni square and Ni square is proportional to T cube. Therefore, I0 will be proportional to T cube. And I0 is proportional to dP and dN also. And dP and dN, they are inversely proportional to T. So therefore, we can write down I0 is proportional to 1 by T. So then we can write down I0 is proportional to T cube as well as proportional to 1 by T. So that comes as I0 is proportional to T square. Equation 17 can be then written as I0 is equal to K1T square into E raised to minus Vg0 by Vt. Equation 19. Now for silicon diode, in the whole derivation we have neglected the generation and recombination of the carriers in the depletion region, which is quite okay for germanium, but for silicon the diffusion current is negligible compared to the charge generation current in the depletion region, which is approximately given by I is equal to I0 into E raised to V by eta is what we have introduced, into Vt minus 1, equation 20, where eta is equal to 2 for small currents and eta is equal to 1 for large currents. For silicon diode, I0 is proportional to Ni and not Ni square. And since Ni square is proportional to T cube e raised to minus Eg0 by Kt, therefore Ni is proportional to T raised to 3 by 2 into e raised to minus Eg0 by Kt. Therefore, I0 can be written as K2 into T raised to 3 by 2 into e raised to minus Eg0 by Kt. Equation 21. Thank you for watching this video.